Hey, take a look around you for a second. That phone in your hand, the chair you're on, maybe the window you're looking through. It all feels so simple, right? So solid. But it's not. Every single object is a battleground of atoms, a universe of choices, all carefully engineered to do a very specific job. So today we're going to pull back that curtain and reveal the secret science that makes your stuff, well, stuff.
Let's start with something we all know, like a car. I mean, it looks like one thing, but it's really an orchestra of different materials all playing together. You've got steel for strength, right? Aluminum to keep it light, glass so you can see, plastics for the inside. Every single piece was chosen for a reason.
Or think about sports. The incredible speed of a tennis serve? That's not just the athlete. A huge part of that is the racket itself. A composite of graphite and carbon fiber, engineered to be both incredibly light and unbelievably strong.
Heck, even a simple cooking pot is a total marvel of materials science. It's designed to get screaming hot without melting and to do it over and over without rusting into your food. So you've got a car, a racket, a pot. They seem completely different. But here's the thing. They all start with the exact same make or break decision. It's the material. Before you can even think about designing something, you have to decide what you're going to make it out of. That choice, it's the foundation for literally everything else, from how well it works to how long it lasts. It is the first and honestly the most important question any engineer has to answer. Okay, so how on earth do they choose? Well, it turns out that this vast, almost infinite universe of materials can actually be organized into just 4 fundamental families. Think of them as the basic building blocks for our entire physical world. First up, you've got the big 3: metals, ceramics, and polymers. The easiest way to think about these is like the primary colors of the material world. Pretty much every solid thing you can touch started out as one of these.
But what happens when you start mixing those primary colors? That's where the magic happens. You get a 4th totally game-changing family: composites. This is where engineers get creative, combining materials from the other families to cook up something brand new, something with properties that are way better than any of its individual parts.
So let's do a super quick rundown of the family traits. Metals, they're strong, they're great at conducting heat and electricity, and they've got that classic shine. Ceramics, like your coffee mug, are super hard and fantastic at insulating. Polymers, that's all our plastics and rubbers. They're known for being lightweight and flexible. And then you have composites, the custom-built superheroes of the group, designed for really specific high-stress jobs. Think airplanes or that tennis racket we talked about.
So, if you're an engineer with a problem to solve, how do you pick the right candidate from these families for the job? Well, you look at their resume. Seriously, every single material has this unique set of properties, kind of like a personality, that tells you exactly what it's good at and what it's not.
And that resume, man, it covers a lot of ground. It'll tell you its density, whether it rusts, how it deals with electricity and heat, the whole shebang. But for an engineer who's building something that absolutely, positively cannot be allowed to fail, we're talking a bridge, a jet engine, an artificial hip, one section of that resume matters more than all the others: its mechanical properties.
This is where you find the answers to the most important questions. How does this material behave when you put it under force? If you push it or pull it or twist it, is it going to bend? Is it going to stretch? Or is it going to shatter into a million pieces? Getting this right is literally the difference between a skyscraper that stands for centuries and one that doesn't.
To figure this out, engineers perform what is, basically, the ultimate stretch test. They take a small standardized sample of a material, lock it into a machine, and just pull it apart until it snaps, measuring every tiny little thing that happens along the way.
And to understand this whole test, you really only need to know 2 words: stress and strain. It's super simple. Stress is the force you're applying when you pull. Strain is how much the material stretches or deforms because of that stress. It's just cause and effect. Stress is the cause, strain is the effect.
Okay, imagine you're pulling on a piece of taffy. The pulling action, that's the tension force, and it creates stress inside the taffy. And how much longer the taffy gets as you pull, that's the strain. Engineers just do this with way more precise machines to find a material's exact breaking point.
And all that amazing data they collect, it gets plotted onto this one single incredibly powerful graph, the stress-strain curve. This chart is basically the biography of a material. It tells the entire story of its life and death under pressure. Okay, let's walk through it. As we start pulling from the far left, you see the line goes up, nice and straight. This section is the elastic zone. Here, the material is stretching, but if we were to let go, boing, it would snap right back to its original shape, no harm done. But if we keep pulling past that yield point, well, now things get serious. We've just crossed a line and entered the plastic zone. Any stretching that happens from here on out is permanent. We are fundamentally and forever changing the material's shape. We keep pulling, and the stress builds until, bam, we hit the very top of that curve. That peak, labeled TS, is its ultimate tensile strength. It's the absolute maximum stress the material can possibly endure. From here, it's all downhill. The material starts to get skinny in one spot, a process we call necking, until finally, at point F, snap, game over. It fractures.
So this makes the difference crystal clear, right? Elastic deformation is just like stretching a rubber band. You let go, and it's back to normal. No big deal. But plastic deformation, that's like bending a paperclip. Once you bend it, it's staying bent. And understanding that one simple difference is absolutely key to designing everything from skyscrapers to soda cans.
So, everything we just talked about, that's the fundamental science that allowed us to build our entire modern world. But here's the really cool part. The story is far from over. In fact, you could say the most exciting chapter of material science is the one we're about to write next.
And what you're looking at here, this isn't some far-off sci-fi dream. This is happening right now. On the left, that's self-healing concrete that can literally repair its own cracks, making buildings and bridges last way longer. And on the right, that's a flexible electronic skin that can give robots a human-like sense of touch. These are the kinds of advanced materials being cooked up in labs today.
You know, there's that timeless saying that necessity is the mother of invention, and that's totally true. But what this field really teaches us is that materials, they are the tools of invention. If we want to solve the biggest challenges of our time, from clean energy to better medicine, we need to invent brand new stuff to build the solutions with.
And if you just take a step back and think about it, this has always been true. We define the great chapters of human history not by our leaders, not by our wars, but by the materials we learned how to master. The Stone Age, the Bronze Age, the Iron Age, every huge leap forward for humanity was powered by a breakthrough in materials.
Which brings us to this one last, really fascinating question. We've defined our entire past by the materials we mastered: stone, bronze, iron, steel. So, what's next? What material will future historians use to name our time? The Silicon Age? The Graphene Age? Maybe the Nanomaterials Age? That choice is being made in labs as we speak, and whatever it is, it will define the world our kids and grandkids inherit.